quickly, so if you don't get something, it's because you're not paying attention and writing stuff down. On number 3, all you really have to write down on number 3, you might want to start on like number 5, maybe start graphing that while I'm explaining some of number 3, because when I start to move real quickly, if you don't have that graphed already, then it might make it so that you don't get it finished. Number 3, all they want us to do is decide what is the vector, the component form of this vector, CD. Remember, your component form is going to look something like this. As I get my pen set up, it's going to have that jagged parenthesis, not just a regular parenthesis, and then you got to count. How much does it go left or right? That's your first number. And then how much up or down. So to go from C to D, we just are going to decide how we move. You can count it right there in your book if you can't see my little squares up here. How much over does it go?
6 or 7.
Which one is it? Look in your book if you can't see it. 7? So what's our first number here? 7. Comma. How much down does it go?
3.
So what's that tell us? What's that down 3? How am I going to represent that? -3. That's all that is. That's the component form of that vector. It tells you right 7, down 3. Next one, again, get this triangle graphed on one of the graphs on your piece of graph paper. Curtis, you heard me say that this is going to be collected, right? Give me 3 points and you're not even with us. There's like 17 or 18 problems we're going to do together. Each one's going to count a point. So if you don't write this one down, that's -1. Does that make any sense to miss that? Austin, does that make any sense to miss that?
Which is that? Number 3 counts 1.
And number 3 counts as 1. Every problem's going to count as 1. Number 5. Number 5, they gave us this triangle. I've graphed it on there already. They want us to use that vector to translate that triangle. Remember, with a vector, what's the first number tell you to do?
Left or right?
Move left or right. What's the second number tell us?
Up or down?
Up or down. So when I go over here to D, you're on your graph. All you're going to do to D is move it how? Which way?
Right.
Right 6. 1, 2, 3, 4, 5, 6. And down how many?
0.
So we put a dot right there. What's that point going to be labeled? D prime. D prime. Now if you have trouble because you drew your triangle one way too far or something, do you always have to draw the X and Y axes right in the middle of the graph? No, so start looking at your numbers and figuring out where do I need to draw it. How about F? What are we going to do to it?
Right 6.
1, 2, 3, 4, 5, 6. Put a dot. What's that going to be? F prime. Good. Do the same thing for E. 1, 2, 3, 4, 5, 6. E prime. Trace the new triangle or connect the dots there. My triangle doesn't look too good. What should be true about your new triangle and the original triangle? They should be exactly the same. Just moved in a different location. Number 8. Number 8 uses this same triangle as we used in number 5. All right, so I'm just going to go back to this original. Instead of having one graph for 8 and one graph for 5, let's just put 8 on the same graph. Make it easy on ourselves so we don't have to re-graph the original triangle. What's this vector tell us to do? Left 2, down 4. So if I start at D here, I go left 1, 2, and down 1, 2, 3, 4. Now, since I put it on the same graph, what am I going to label that point? Can I label it D?
Double prime?
Use double prime. Just use 2 of the little apostrophes. Do the same thing to the others. How do I move from F? Left 2, down 4. 1, 2, 3, 4. That's double prime. E, left 2. 1, 2, 3, 4. E double prime. Connect those two. I probably should change colors, but it doesn't matter. Does that triangle look exactly like the other two? It goes. Next one, look at problem 12. Problem 12. You don't have to graph this one. All you're going to do is write these answers down. Now on problem 12, they didn't ask you to write the vector. They just asked you to write the rule. We're going to write both. We're going to write both. Looking at problem 12, what's the name of this point right here? If it would stay on that slide. What's the name of that point right there? Say it again. M. What's the name of this point? Do we really have to check all of the points to see how it's moving? No, just one of them. So I picked M and M prime. What did I do to go from M? So what's our vector going to say? 3, 1. Write that down. That's your vector. Tells you you move to the right 3, up 1. Now to write the rule, remember your rules look like this. X, Y goes to something. What's this vector telling us to do to each X coordinate? Add 3. So what do I write right here in this first part? X plus 3. It's that simple. What's this vector telling us to do to each Y coordinate? Y plus 1. That's supposed to be a comma there. So this is the vector telling you how that shape's moving. This is the rule telling you how that shape's moving. That's answer number 12. (13). Nothing to graph on 13. You could graph if you wanted. We're not going to. What is the image? Remember, pre-image is what you start with. Image is what you end up with. What is the image of 2, 6 if we're doing this rule right here? What's this rule telling us to do to every X coordinate? Subtract 8. So this is going to be A prime. What's the X coordinate for A prime? What do we do? -6. How'd you get -6? Make sure everybody understands it. 2 minus 8. So the X coordinate of this new A prime is going to be -6. What's the Y coordinate going to be? 6 plus 4, which is 10. Now be careful on this one. This time we're, instead of looking for the image, we're looking for the pre-image. Pre-image. You gotta write as I write, because I'm not gonna wait. So you gotta stay caught up as we go. Because otherwise, Curtis, this doesn't make any sense for you not to get these points. This is easy stuff, you're just copying it down. Okay? So we're looking for the pre-image. So they're telling us where we ended up at. We want to know where we started from. So we're just looking for C this time. How can we do that? If here we started and then went to here and we subtracted 8 to every X and added 4 to every Y, what are we going to do if we're going backwards? Instead of subtracting 8, what would we do? Add 8. So what's -3 plus 8? That means we started at 5. What's -10? Instead of adding 4, what are we going to do? -14. So our original point this time was 5, -14. And then we took that to -3, -10 by using that rule. Next one on problem 17 and 18, we're just gonna find the coordinates, we're not gonna graph them. So just write down 17 and 18, or write down 17 there on your paper. And we're just gonna find the coordinates of P prime, Q prime, and R prime. We're not gonna actually graph them like they said to do in there. So when we're looking at P prime, and I'm just gonna write this down real quick. We got P prime, we got Q prime. You could probably, that's a crazy prime mark there. We got R prime. When Chloe writes this down, she's not gonna put the crazy prime mark, right? And think that that means something special. What's this rule telling us to do to each x coordinate? Add 4. What's it telling us to do to every y coordinate? Add 6. So when I add 4 here and add 6 here, what's that going to give me for our new P prime?
2 and 9.
2 and 9. Everybody agree with that? How about Q prime? We should be able to run through these pretty quickly.
5 and 8.
Everybody agree with 5 and 8? I'm not even looking over there, so I hope Evan's right. Everybody agree with that? How about R prime?
7 and 5.
7, 5. We'll write down the same thing here. P prime, Q prime. This is a completely different graph this time. And R prime. What's the new rule? The rule on 18 telling us to do to every x coordinate? Add 9. How about the y coordinates? -2. So we go back up here. Add 9 to that, what do you get? 7. Subtract 2 from that, what do you get?
1.
That's the P prime for 18. What's Q prime going to be?
10, 0.
10 what?
10 and 0.
0. Everybody agree with that? Yeah. How about R prime?
12 and
Everybody agree with that? 12, -3.
yeah.
Get both those. Good. Next one, and this one you have to graph. I'll give you a second. Go ahead and graph this triangle. Is it going to help you if I write down the coordinates of x, y, and z? Would that be helpful? All right, so let's figure it out. What is x? 2, 4. What's y? 6, 0. What's z? 7, 2. Everybody agree with all those? So graph that on your graph real quick. We're going to do a composition this time. What's a composition? How's that different than all the other stuff we've been doing? All right, you're doing more than one thing to it. So we're sliding this shape one spot, then sliding it somewhere else. So how many triangles are we going to end up with on our graph when we get done? 3. What's the first translation tell us to do to each thing over here? Right, which way?
Left.
Which one is it? Left 6 and then what?
Stay.
Stay the same there, right? So left 6 down or up 0. So all we're going to do is on our graph, how am I going to move the x?
Left 6.
1, 2, 3, 4, 5, 6. What are we going to label that? What are we going to label that? X prime. Do the same thing for the z. 1, 2, 3, 4, 5, 6. Do you really have to be watching up here now at what I'm doing? Could you be doing it right there on your paper? 1, 2, 3, 4, 5, 6. Y y is right there, or y prime, I'm sorry. That's our first triangle. That's doing this first translation. Now, once we have it there, a lot of people getting confused on this. Do we go back to the original shape? No, we moved it to there, and then we're gonna move that shape somewhere else. What's this second one tell us to do to that second shape?
Right, 2 up 7.
So we go to the right 2 and then up 7. So I count 1, 2, and then up 1, 2, 3, 4, 5, 6, 7. What am I gonna label that new point right there?
X double prime.
X double prime, very good. Do the same thing for the other 2. Right 2, up 7. 1, 2, 3, 4, 5, 6, 7. That's going to be Z double prime. Right 2, 1, 2, 1, 2, 3, 4, 5, 6, 7. That's going to be Y double prime. Connect the dots there. Those are our triangles. Once Bree gets this far, she graphs this purple triangle that I have. What should be true about it and the blue triangle?
Same thing.
They should look exactly the same. So if her triangle ended up looking like that, then what's she know?
It's wrong.
She messed up somewhere. She probably counted wrong. Go back and fix it, right? What's that? Huh? So you had the original one. So if there's not enough room, just come out to the side a little farther. (23). They want us to describe this composition. You don't have to draw the graph here. All we're going to do is describe it. So we're going to have 2 parts. The first part, what shape to what shape are we going for the first part? Blue to red. Does everybody agree with that? Do we want to? How do we want to describe it? We want to use the rules, or do we want to use vector form? Vector form because it's shorter. All right, doesn't matter to me. So we're going to have something like this for vector form. Those 2 jagged parentheses and then 2 numbers. Pick a point in the blue one. A, B, or C? A. How do you move from this A to that A prime?
Right 5 up 1.
Does everybody agree with that? So what goes right here?
5.
5. And what goes here?
1.
So that's the first one. Now the second one. What shape are we moving from now? We're moving from the red to the green. Chloe said she wanted to use B. Does it matter which point we use?
No.
No. So if I want to use the B, and I'm going here, oops, not too far, here, and then down to there. Can't hardly tell that, but how did I move?
Left 5. 5 and 6.
So what do I write? -5. -6. Everybody agree with that? So that's our vector for our first movement, our vector for our second movement. Is that right? Bree's looking at like she doesn't trust you guys as far as your counting goes.
That's supposed to be -5. I don't.
Yeah, it's
I think
-5.
6. Yeah, it's -5, not -6.
This is supposed to be -5?
Yeah.
Quit complaining, Curtis. I don't even feel like hearing you complain. You're writing down about half of what we're doing. So don't complain on the stuff that you decide to write down, that's just silliness. Everybody agree with that? Hopefully Austin's getting all this. Alright. On this, what I want you to do, we're gonna graph, this is on page 186, flip over in your books to 186. We're gonna graph number 8, and I just got lazy and didn't feel like making a new slide. Then I'm gonna erase my slide, then we're gonna do number 10. So what I want you to do right now is just graph that triangle JKL for number 8 on yours while I graph mine up here. So pick one of your graphs. Now, so that Curtis, because he's up here getting frustrated when everything doesn't work out his way and his triangle went off the graph, can you look right here before you draw your graph and see what you need? Yeah, if we look at this, now we go to left 3, to the right 5, down 2. Do we need to be any place really special on this graph? No, it looks like our numbers are pretty normal, right? No, nothing, no 10s or 12s or anything in here. So we should be able to graph it. We should be able to just maybe draw our graph, draw our X and Y axes right in the middle. Sometimes you can't do that. Sometimes you got to decide, hey, I don't want to be right in the middle. So take a second and graph that. Graph yours, your triangle looks something like mine.
Okay.
Now this time we're reflecting, remember, don't let this confuse you, in the y-axis. That just means same as over, right? So we're reflecting in the y-axis. Which one's the y-axis? This one? This one?
Yeah.
So all we got to do to graph this, I'm going to change my ink color here so that it looks different. Let's go with green, maybe. Get it to work. There it goes. What do I have to do to the L to decide where it's going to go when I reflect it over the y-axis? Count. How many spaces is L from the y-axis?
3.
So what's it? What do we? Where do we want it to go?
Right 3.
Over this way, 3. What's this point going to be labeled? L prime. What do we do with the J? Do we count it right? 3 that way?
Go left.
This time it's going to flip over to the other side, right? How many spaces? 5? Everybody agree with that? What's this point going to be labeled?
J prime.
J prime, good. How about K?
Left 1.
1 this way?
How far did you go around J?
Look like 5. 1, 2, 3, 4, 5. So we come back here and we go over this way 5. Connect those. Does that look the same as the other shape? There you go. There you're sad because Caleb has something here. That's what it is.
No problem. Yeah, I miss when he's here, cause then he lay off me a little bit. Start picking on him more than picking on me when he's here.
Not picking on you. Have I been
Right.
picking on you today? I'm trying to get you to do what?
Work. Graduate, pass this class.
Get out of here.
this class.
Exactly. Does everybody have that? Next graph that. While I'm erasing mine, graph that. That new triangle on another graph. So for number 10, graph it. Again, I look at it, we got -4 is a y, so we need to go down 4. Doesn't look like anything really out of the ordinary, so when I draw my graph, I can probably put it somewhere close to the middle. Doesn't have to be exactly in the middle or anything. I didn't feel like moving, so I put my y-axis going right here. Graph it. Do that every time. See me count wrong up here at some point when I'm graphing something, please tell me, because it's sort of hard to see the squares when I'm this close to the screen. That's an L. Everybody's triangle looks something like that one?
Yeah.
This time, a little harder here. We're not going to do much like that one because, Kenneth, should you be able to count and do that stuff by now? Yeah, that's not what we're here for. We're here to teach you something new, right? So we're going to do a whole lot more where you're reflecting in some line or in y equals x. So you've got to know how to do these. So Hunter's going to perk up right now and listen closely so we make sure that we understand how to do these kind of problems. What kind of line is x equals 2? We talked about this in the notes last class. There was 2 different kinds of lines, right? X equals 2 and y equals some number, right? Horizontal and vertical. Which one is this? You got to be careful because everybody messes this up because the x-axis runs horizontal, right? So everybody thinks that that right there is going to be a horizontal line. It's the opposite. So this is actually going to be a vertical line. And what you do to find that vertical line is you go to where x is 2. If I'm standing right here at 0, 0, where is x going to be 2 at? How do I have to move? Up 2? Over which way 2?
Right.
Over to the right 2. This right here. Alright? What kind of line did we just say x equals 2 is? So what do I want to draw in right there? A vertical line. So draw that vertical line on your paper there. My pen's getting off, so it's messing up. So you're going over that line. Now where a lot of you are going to get messed up, how far is K from that line? 1. Not 3, because we're not going to the y-axis. So forget the y-axis and the x-axis even there. We're just reflecting over that line. So if K is 1 space to the right, where do we want K prime to be? 1 space to the left. So we come over here 1 space, and that's going to be K prime. What are we going to do to J? Take it over to the right, and what's it do? Or what's it going to be labeled? J prime. What do we do to L down here?
Right 2.
So we go over this way too. Need to readjust my pen. That's going to be L prime. We connect those. Hopefully your picture looks better than my picture. Does that new triangle look the same as the original triangle? Yeah, it's just flipped over. If you have to, try to imagine stuff. You see me cutting out shapes and stuff up here all the time. So what we had was we had some triangle that sort of looked like this time. Does that sort of look the same?
Yeah.
And all we're doing is reflecting it around that. When we got done, did it sort of look like that? So maybe take your pencil or something and cut out a little triangle and look at it and see, hey, is that gonna make sense? Next, write the new coordinates. Go ahead, I'll give you a second to graph this. Do we need to find the coordinates again? That'd be helpful. What's A? What's coordinates for point A up here? Nothing, just go on the next one. Everybody miss this one? 6, 3. Everybody agree with that? 6, 3. Yes, no, maybe?
Yes.
That's not right. What's B? What's B?
One.
One
negative
down
two.
two.
What's C?
4, 1.
4, 1. Let's go back to A. 6, 3 is not right.
6, negative 3.
Thank you. Graph that on your graph. The blue triangle up there, that's the coordinates of the blue triangle. We're going to reflect it in y equals x, that line. We're going to talk about that. Again, these are the ones you got to know. You probably need to, as I'm walking around just talking now, you need to get your notes out, because there's no way you can do this without the rules that you wrote down last class, or last time I was here. There's no way you can do this, so you need to, once you get it graphed, grab your notes out and start trying to find those notes from last time. If you can't find them, then we'll skip this problem, everybody can miss it. We're doing a reflection over y equals x. Last time we had a rule. Said if you're reflecting in y equals x, it goes xy to what?
So X, Y is. There's two X, Y, Y.
We're doing y equals x. We're reflecting over the line y equals x.
There's the Y axis. To the X axis. So X, Y.
Nah, they ain't got nothing to do with either one of the axes. It's y equals x.
Oh, X, Y is the.
What is it? Y, x. So what's it doing to each ordered pair? It's switching the order. Now, with Chloe sitting here, she's not looking it up in her notes, and that bothers me quite a bit, because when it comes test time and we need to do this, are you going to be able to do any of this without these rules? No. And some of you are going to think that you can, and you're going to mess it all up. All right? So we're going over this line. Does anybody know what this line looks like?
Is it, origin?
All right, so it goes, look at, it says y equals x. So if I said x is 2, what's y? 2. So I go out 2, up 2. Out 3, up 3. Out 4, up 4. It's going to be that line that cuts the graph in half diagonally like that. So that's the line we're reflecting across this time. Yep.
Probably top it down.
So y equals x.
Yeah, I'll get it off the middle. Alright, fine.
What's our A prime going to be? Can we just look over here and count like we did on the others?
No.
It's not going to work that way. If you try to do it that way, you're going to mess it up. So we got to find A prime, B prime, and C prime using the rules. What's A prime going to be? What's that rule tell us to do?
Switch it, so it'll be -3, 6.
Negative 3, 6. Let's just go ahead and find all the points and we'll graph them. What's B prime gonna be?
-2, 1.
-2, 1. What's C prime gonna be?
4, or 1, 4.
1, 4. Now can we graph this new shape? And you should be graphing it on your graph. So we got, you should get the same thing, and make sure you're labeling your points with the A primes, B primes, and C primes. Graphing it right now because I'm going to give you about 5 seconds once I stand up, and then I'm erasing mine. Is that what yours looks like when you got done?
Yes.
I count wrong or something?
Nope.
Yeah, Chloe's working on sitting out in the hallway and looking through the door to write all this stuff down.
I'm not doing anything.
Does that look right?
Yes.
5 seconds. Then I'm changing it. Said we were hurrying, right? 3, 2, 1. Gotta stay caught up. Next one, draw or graph this. Let's go ahead and find the coordinates here. Somebody help me out. What's A?
1, 2.
1, 2. Everybody agree with that? What's B?
4, 2.
4, 2. Everybody agree with that? What's C?
3, -2.
Graph that. I'll give you about 20 seconds or so to graph those points on the new graph there. What's different this time?
The X is negative.
Instead of y equals x, now we're graphing, or we're reflecting over y equals negative x. So we're probably going to need that rule from the notes here in a minute, right? The rule's going to look something like this. It's going to go x, y, and it's going to go to negative y, negative x. Anybody else agree with that? Make sure Austin didn't write it down wrong in his notes. Anybody else got that? That's right. So what are we doing to each one of these ordered pairs this time?
Make them negative.
We're switching them, and
Make them negative.
now be careful. Don't say making them negative, because that's not true. Because what if they start off being negative? So it's the opposite. So we're doing the opposite of each one. So what's A prime going to be? Flip them around and do both. And what Chloe just did, that's what most people, that's where you're going to make a mistake. You get in a hurry, and you forget to flip them, you make them both the opposite or something. You don't do both steps. You got to make sure you do both. So what's it going to be again? -2, -1. Should you be able to do B prime and C prime and then graph it? -2, -4. +2, -3. Now, as you're getting ready to graph these, what I'm going to tell you, that last line, we figured out that last line went down through here this way. Where do you think the line y equals negative x goes? It goes the other direction. It goes down through here like that. And the other reason that we know, if x is 5, what's y going to be?
Other 5.
If x is 5, y is going to be -5. So if I go out to where x is 5, 1, 2, 3, 4, 5, down 5, it should be this point right here that I completely missed with my line. What if x was -2? What would y be?
Positive 2.
So we go out this way, -2 and up 2. Again, I missed the point completely. It's gonna be the line that runs down through there. Now we graph these, and again, once I get up from my graph, you should have your graph done, so if you don't, I'm switching the slide. I'm not waiting on anybody this time. -2, -1, that's gonna be A prime. -2, -4, that's gonna be B prime. And then 2, 3, 2, I'm sorry, 2, -3, that's gonna be C prime. We connect those, does that triangle look like the original triangle?
Yes.
Yeah, it's just reflected across that new line right there.
I got it.
Draw these 3 shapes.
Where?
Somewhere on that paper. On your forehead.
Alright.
That's all right, we'll staple them here in a minute.
Stop.
Draw those 3 real quick.
That was just easy.
Somebody come up here and with my pen, draw me the line of symmetry for 21. Go ahead, Hunter.
I'll go down to the next one.
I wanna do 22.
I have to change this one, so like, what, this?
Yeah, no, this, yeah. Does everybody agree with that? Remember, with the line of symmetry, what has to happen?
It's gotta be equal.
It's gotta be the same on both sides, but not only does it have to be the same, when you fold it, what has to happen?
That's too like.
They gotta match up perfectly, alright? 22,
Don't do that.
give me one of them, alright, Curtis? Just one, draw in one line of symmetry.
You just gotta push this button right there.
Yeah, you don't have to push any button.
Alright, cool.
Does everybody agree with that one?
Yeah.
Give me another
I know
one.
what I
Alright,
said.
Bree.
It's all on line. That's wrong.
Does everybody agree with that one?
What?
Curtis, shh. We don't need your comment every time. Is there any others? Alright, Austin, give me one.
Dude, I have to line pretty close.
I don't know, does that work?
Probably not.
I'll tell you what, let's, got the shape right here. Let's look at it and see. Again, did Mr. Eversole have to make this shape for him? No, because I probably knew what the answer was before, right?
You already folded it.
So I make this, and what Austin's up there thinking about, he's going, well, I wonder if I fold it from corner to corner here, if it would match up. Are you talking about these corners? One where my fingers are, or are you talking
Yeah.
about these corners?
These corners.
Those corners? Alright, so if I fold it there, let's see if it matches up.
I knew it. Wait, so you do it on both sides or not?
I don't know, draw in one of them.
Like, does it count on both sides? 'Cause it's technically the same thing.
No, it's not the same thing, because that's one of them. So where would the other one be?
It's ours.
Go in the other direction. Would that work? Yeah, so draw those on your paper if you haven't already. How about 23? Who wants to come up and do 23 for me? How many lines of symmetry did that one have? This one had 1, this one had 4. How about 23? Somebody come up and do 23 for me.
Where would that go? Oh, I'm gonna try. I got one. If he doesn't.
Does that work? How about that one? Does it work? Why not?
Because both sides are equal.
Because the corners are like, don't even know
Because
what,
like,
how do you?
it's like tilted.
If it was a square.
It's tilted?
Cut it.
So it doesn't work if we have a parallelogram that's gonna go that way?
Cut it.
Alright, go ahead.
You both of them?
Sure. Is that gonna work?
No.
That's not gonna work.
Yeah, you showed us in class last time.
Alright, you know
Is
what?
it gonna fold and match up?
No.
It's gonna be off, isn't it? So what is it? None. That's what you should write on this one. So on 23, write none. There are no lines of symmetry on 23.
That's dumb.
Are no lines of symmetry on 23. You're going to, if you need a stapler, there's a stapler right here. You're going to make sure your names are on those papers and lay them right there on that desk. When you get back to your desk, you're going to start to copy down these notes. So move quickly. We're going to stay on this notes page about the next 15 seconds. 14, 13,
Hey.
12, about to say 11, can't count. 11, 10, 9. If it doesn't work, tap it on the desk and then it'll start to work. Right, quickly, rotations, what we're going to cover today. Be able to perform rotations and compositions. What's a composition again? What's a composition again?
Adding two or more transformations.
2 or more transformations. So we're going to do not just one thing, but 2 things. Right, Curtis? Quit looking at everybody. So we're going to do those. Identify rotational symmetry. Now, because we're probably going to run out of time as usual, so I'm going to sort of go over rotational symmetry right now. Rotational symmetry is if I take a shape like this rectangle right here, right? And I have something on it, a pin. Last night when I was building something and I used a nail to put in the center of my shape. So I put that right there in the center. My son was helping me build something. He built one thing and I was building another. He used a screw. I put that right there in the center. And then rotational symmetry is the degrees that if I turn this, it looks exactly the same. So tell me to stop when it looks exactly the same as it does right now. How many degrees did I turn that? 180. That's what you'd write down. This shape has rotational symmetry at what turn? 180 degrees. All right? Now, I was always taught that it also has rotational symmetry at 360. So it had 2. But this book, for whatever reason, says don't go higher than 180.
Well, I mean, it really could have.
All right.
You could just continue to make.
Right, so you could do like 180, 360, then 540, then 720. All right? And when you get to higher level maths and sciences, you will do that, because if you're dealing with something like a pulley or something, is it just going to turn once and then stop? No, it's going to turn and turn and turn and turn. A pulley. Or a wheel. Right? So that's rotational symmetry. Now with rotational symmetry, the other thing I'm going to say, if we were learning out of the old books that we used to have, what we would say is that this has order of rotational symmetry of 2, because it looks exactly the same twice throughout one term. All right? So the order of rotational symmetry would be 2. So that's rotational symmetry. Again, for rotational symmetry, you're just going to write down like 180 degrees. It looks exactly the same. All right, write these down. A rotation is a transformation where a shape is turned about a fixed point. These 3 things are what you need, the information you need to know to do a rotation. Now I'm going to tell you that this book, for whatever reason, does not do clockwise rotations. but we're going to learn how to do clockwise rotations. Alright? The book does everything counterclockwise. And the reason for that, if I turn this piece of paper, if I grab my piece of paper again, and I put a mark on it, I put an X right there, forget the other stuff that's on there. And I say you want to turn this 90 degrees. I got to turn it around this way so I'm not telling you wrong. 90 degrees clockwise. It ends up looking like that. Well, if we wanted to do the same thing going counterclockwise, instead of turning it just 90 degrees, we would turn it 270 degrees. So going clockwise and counterclockwise could end up being in the same spot, just a different angle of rotation. So they do everything just one way. They do everything counterclockwise. So when you're doing the homework for tonight, it's going to be, they're not going to tell you a direction, but everything's going to be counterclockwise. Now the bad thing with counterclockwise and clockwise is, does everybody know which direction is clockwise and counterclockwise? No, because all clocks look like that now instead of that, right? So clockwise goes that direction, counterclockwise goes the other direction. And you'll see me when I start to do these problems, I have to draw the arrow. Okay, I'm going clockwise, and I'll draw the arrow up on top of the paper or something so that I can remember, hey, I'm going that direction. 3 things you got to know. You got to know the center of rotation. Normally our center of rotation, you probably want to write this down, and you've probably done, if you've ever done rotations before, you probably used this. Where do you normally put the center of rotation at? The origin, 0, 0. That's what we're going to do most of the time. A lot of the stuff we do will be about the origin. Our angles of rotation. How are we going to rotate things? Are we going to rotate it like 54 degrees? Probably not most of the time. What are the numbers that are more used? 90 degrees is one. 180. 360. We missed one.
240.
Close. 270 and then 360. Everybody likes 360. How come?
Because it's just long.
It's all the way around. So when I say, what side is this X going to be on when I rotate it 360 degrees? It's going to be in the exact same place, right? So everybody likes 360. If I rotate it 90 degrees, that's a quarter of a turn, right? Something like that. If I rotate it 180, something like that. So if the X started on the bottom and we rotate it 180, where would it end up? 270. 270 is just another quarter of a turn, right? So if that's 90 degrees, this is 180 degrees.
That makes sense because 9 times 3 is 27.
So you got 90, 180, then 270 is 3/4 of a turn. And then 360 is a whole turn. So 270 is just a number that we don't usually use, but all you're doing is saying 90 here, then adding another 90 for that quarter of a turn, then add another 90, then add another 90. All right, what I need you to do, walk up here, and you're going to grab worksheet and a protractor. I'll do seats today, but I don't have time. Worksheet and a protractor. When you get back to your desk, you're going to listen closely. This is what you tried to do last time. We're going to go over it. And I want you to listen to this so that you sort of understand it. It's not something that we're going to do a whole lot with. I'm not going to expect that you can do this exactly, but we're going to, something you need to know how to do just in case you're ever going to do something like this. The first one looks like this, and we're going to rotate it 90 degrees counterclockwise. Again. First thing I do, it says counterclockwise. First thing I do, I come up here top of my paper and say, okay, I know I'm going that way, because that's counterclockwise. So I mark that down, that way you'll see me looking up at it every now and then to make sure that I'm going the right direction. Now this is what you're gonna do. And I'm probably gonna erase all this here in a minute. You're gonna connect point A to point P. Before I do all that, what we're actually doing, it's like we're tethering this triangle to that point. So we're putting a point right in the center of the triangle, which we can't actually find right now because we don't know how to. But we're putting a point right there, and then we're going to rotate this 90 degrees counterclockwise. So this triangle, if this was my triangle, it's going to rotate counterclockwise a quarter of a turn. Right? Does that make sense? The way we can do that is tethering this to that. Does everybody know what tethering means?
No.
What's a tether ball?
It's like when it goes around.
It's a ball that's hooked with a string to the pole.
It just goes around.
Alright? And all we're doing is we're tethering that to it. And if I tether this to a string and I move it like this,
It's gonna keep going.
it should stay the same, right? It's just going to sort of spin around there. Okay? So that's what we're doing here. Now what I want you to do this, we're going to attach point P to point A. So just drawing a line, and notice my lines aren't very good. So do I expect that yours is going to be real spectacular? Probably not. Then you're going to do this. How far do we want to turn it?
90.
So you take the point of your protractor and you lay it right on that point P. And we line up this line that we just drew with the black line on your protractor. I can't find my point. Oh, there it is. I'm looking, trying to look through the hole instead of just looking at where it's. So something like that. Does that make sense? How far do we want to turn it? So guess what I come up here and do? Put a mark at 90 degrees. Then we're going to do this. We're going to make a line that goes out through that mark. So when we turn this, point A is right here. When we turn it, we want point A to end up over here on that new line. That's where it should end up at because the way it's tethered to there. How do we figure out where it's going to end up at on here? Is it going to be right here? Here? How do we know? We don't. So what we do, if we attach the string to right there, what should be true about the distance P is from A and the distance P is from A prime when we put it on there?
Same thing.
It better be the same thing, right? So this is all I'm going to do. Take your protractor, put one corner on there, put your fingers right here on P. It's going to be that far, isn't it? So I'm just going to measure up here about that far. Don't even measure it. Just use your fingers. Right? Maybe Lexi's looking at it and going, what? Then Lexi could do this. On your little paper, could you use your pencil and just do this? Say, okay, A is that far. Mark it with your fingers and just do it that way. Don't label it. You see, you guys, you got confused, Curtis. You were understanding it because now you all of a sudden want to actually use this to measure. I don't want you to measure. I want you to do this. Put the corner on there. Put your finger right there. It's about that far, isn't it? That's all we want. Now you come up here. Put a dot right there at the end of the protractor. That's where, so right there on that line, that's where A prime is going to end up. So, well, no, we just put A prime in there for right now. Now we're going to do the same thing for B and C. My stuff's not long enough. I go from B, I don't even really need this. Go from B, you're going to draw something like that. Ooh, that's horrible.
Wait.
So put B to P.
B to P. How'd I get A prime?
Yeah, how do you get that right?
So, look, if it helps you do this, I take my fingers, it's that far, isn't it? From P to A. That's how far I want it to be. A prime is going to fall on that line that far up.
So, does that have to be exactly?
Well, not really. I mean, I gave you the protractor so we could try to be exact, but we're not going to worry too much about it. Now you connect B to P. And we want a 90-degree angle again, right? So you put your protractor on there, put the hole right there on that center point, line up that black line with that, go up here to 90. And now we're going to go up. So B prime is going to fall on this line somewhere. Did I go too quick? So look, connect P to B. Okay? Got that? Now you do this. Lay the hole right on P again. My hole. See how my hole's right on P? Line up this line. My line's way crooked, so line up this line that we just connected B to P with. Keep slipping. And then we go up here to 90, put a mark, and then we draw in this line. So what we're doing, it's like B's coming here, maybe this will help. We're shooting B through a tube. Alright? It's coming down here, it's hitting P. How's it going to reflect off? So it goes. Where's B prime going to end up? Somewhere on there. Right? How do we figure out where B prime is at on there? Do we just guess and say, oh, it's right about there? You measure it again. So this time I'm going to use my, back on track here, Curtis. This time I'm going to use my yardstick. Notice, am I reading the numbers on the yardstick? No, I'm just putting that right there. Coming down here to P, using my fingers. Hey, it's that far. I don't care how long that is. We're not being that exact. It's that far. So now I go here, right where my fist is. That's where B prime is going to be. Guess what I do for C? Same thing. Connect it to P. Line up that hole in that line. And we want to go, so it's 90 degrees. 90 degrees is going to end up somewhere like right in there. Then I'm not even going to draw the line for C prime this time. I'm just going to measure it and go straight up there. It's about that long. So then, if I can get my yardstick to work here, come up here about that far. It's going to be at the end of the yardstick, somewhere about right in there. My pin's way off when I get that high, so it doesn't work out so good. Guess what I do with those 3 points now? Connect them.
That's so much work.
Does that look like the original triangle, if you could see it? Now, were we real exact there? No. Could you be real exact if you needed to be for whatever reason? Yeah. You just got to have the correct tools. Pretty easy stuff, everybody thinks? Let's try the next one. Let's connect P to A. Look, this time I'm going to try not to even, I'm going to try not to use my straight edge and everything. Let's see how close I can get. So I connect P to A. This time we want a 60 degrees clockwise turn. So let's come over here. How many degrees is that? About 90, right? 60, about 2/3 of that. Does that look like a 60-degree angle? Yeah, somewhere close. So we take this. I lied. I'm going to use it because I'm too chicken to try it. I think that's a 45.
Yeah, why is yours so like so small?
Do what?
That's not even close to
Hey, but I think
Yeah, yours is definitely really
That's
small.
like a 37.
That?
Yeah.
You're in the middle.
How big is
Watch.
I think
Look.
it's alright. Yeah.
Look, was I pretty close?
Yeah.
Oh, that was
I was-
almost exact. It was like
I
61.
was saying,
Oh,
I was on your team
I know. So we were right, Curtis. Evan.
Curtis was right. You were right.
I said it looks right.
So we go 60 degrees here. We come up here. You gotta be careful. Do I want this 60 degrees over here?
No.
No, we're turning it this way. We want this 60 degrees, which on my protractor actually says 120. So we got that. That's our angle. So A's coming here. It's hitting P. It's going to shoot up here somewhere. We take our, I'm not even going to use my ruler this time. I'm going to do this. About that long. About that long. We're going to make that A prime.
A prime.
Connect C to it. We want 60 degrees. Lay this on there, find 60 degrees. If I can get it laid on there right. Find 60 degrees, gonna be somewhere, let's see, oops. What am I doing wrong here? 60 degrees from there. 60 degrees is gonna be right about here. So C is gonna end up somewhere on this line. Let's measure it again. We're about that far, about this far. That's going to be C prime. Let's do B. Where'd you get lost at? You did you do A? So now at C, we connect it to P, right?
C.
Then we go up here, lay our stuff on there, 60 degrees. Ooh, oh, my 60 degree angle did off so far. I'm at 50 degrees. 60 should be somewhere like in there. I don't know how I got off so far. Measure 60 degrees. Come out here. Oh no, I was about right. I was looking at the wrong line. I was looking at the wrong line, wasn't I? And then we put C prime about that far out. Same as the other. I measured it using my fingers here. Do B. Connect B to P, which I just did. 60 degrees going up this way. 60 degrees going to be somewhere about in here. So B is going to fall on that line going up through there. We want it to be about, get out my yardstick so I can sort of measure this. B is about that far from P, so B prime should be about that far. It's going to be way up here, right? Somewhere way up in here. That's going to be B prime. Connect those. Does this triangle, does that triangle look about the same as the other triangle? Does this triangle look about the same as this one? Just rotate it around. Now again, Kenneth, am I going to expect that you can do that perfectly? No, but it's not something, if I went home and asked my son who's got an architecture degree to do this, he could figure it out pretty easily because he's done it. All right? Something that at some point, Hunter sitting back here, if he gets an architecture degree, he's probably going to need to know how to do that, and he's going to work a little harder at it probably then. All right? All right, set that off to the side. Yep. Back to your notes. Go ahead and copy this down. Kenneth, can you do me a favor and reach up there and turn the light on? Because this is hard to see. I'm going to move that box so that you can see it all. Now, can everybody see? I was going to have Kenneth open up the door too. By that, can you see?
No, it's fine.
These are the rules if you're rotating on a coordinate system about the origin, 0, 0. These are the rules you're going to use. Write them down carefully. If you mess them up, as you write them down, then you're going to do every problem wrong when you use that rule. Again, this book only does the counterclockwise ones. Doesn't do the clockwise ones. And the reason for that, look at clockwise for 90. You see that anywhere else on here? counterclockwise for 270, right? So it's the same turn, you're just going in a different direction. You end up with the same thing. What do you notice about the 180s? They're the same. So in other words, if I turn this 180 degrees clockwise, or I turn it 180 degrees counterclockwise, doesn't matter, it ends up in the same spot. And what do you notice about 360? They're the same also, because 360 just ends up being right in the same spot. This part up here, what I'm saying when I'm saying this up here, Austin F back here is graphing this right here, and he wants to rotate it 90 degrees clockwise. All right? So, I gotta look at it this way to make sure I'm turning it clockwise. So, he looks at his paper, and he's sitting there looking at it, and he goes, oh man, I don't know. Can he do this? Can he turn his paper like this 90 degrees and see what the new shape should look like? And that's what this is saying. Just use your paper. Once you graph the original, take your paper and actually turn it to see what it's going to look like before you go to give an answer. When I rotate this piece of paper, do I change the rectangle in it? So remember we said that then it's a rigid motion. Since it doesn't change any, it's a rigid motion. What if I gave you a point? Make up a point for me, Curtis.
0, -2.
Let's use something other than 0, sir.
5 and -2.
5, -2. We were going to rotate this point 90 degrees clockwise. What's that 5, -2 going to go to? What's it going to become?
2, -5.
Yeah.
2, -5. Everybody agree with that?
2, no, -2, -5.
-2, -5.
What is,
Because it becomes
Alright?
negative. when
Because
it-
you switch the two around,
But it was already negative.
and the A that goes to the second spot is the opposite of what it started to be. But the B, did it change signs? No, it stayed the same. What if we wanted to do that same point counterclockwise 90 degrees? What's it going to go to? Say it again. Look at our original point, 5, -2. We switch them. Do one thing at a time. Switch them. What's it going to be when you switch them? Switch those two around. What's it? -2, 5. Then, what's it tell you to do to that first one now? Change the sign. So what's it become? +2. Does it tell you to change the sign in the second one? So what's our new number? 2, 5. You gotta be real careful when you're doing this. Especially since, are you gonna have one point normally? No, you're gonna have like 3 points on a triangle or a rectangle or a pentagon or what, 5 points on a pentagon, something. So you're gonna have to do it to all of them. And you're gonna get in a hurry, and then you're gonna mess up the rule. You have to be able to use these rules. Let's do a hard one. What if we had Curtis's point at 5, -2, and we wanted to rotate it 360 degrees counterclockwise? 5, -2. Ends up being the same spot, right? Got to be able to use these rules. If you didn't write these rules down, you're going to be able to do this? Probably not. I have to look up, I teach this every year, and I still have to look up the rules every year. Skip this. All right, write this down. Rotational symmetry. Rotational symmetry. Can you guys see that without me moving that box? Figure has rotational symmetry when it looks the same when turned less than 180 degrees, about a point at the center of the figure. That's what we were talking about at the beginning when I poked my pen through this piece of paper. Alright? When you give your rotational symmetry, what you're going to do is you're going to give the number. How much of a turn did it make? 90 degrees, 180 degrees, 60 degrees, 20 degrees, whatever it comes out to be. Order of rotational symmetry. I don't even think this book deals with order of rotational symmetry, but I'm going to talk about it because I think it's important. Order of rotational symmetry is that the number of times the shape looks exactly the same when you turn it one whole turn about that point. So if I had this shape right here, what's its order of rotational symmetry? How many times does it look exactly the same? One. It only looks exactly the same that one time. What's the rotation? What's the angle of rotational symmetry? Is it ever going to look the same in a half a turn? No. So it doesn't have any rotational symmetry. All right. So it has no rotational symmetry. That point that I poked in here, what's it called? Center of symmetry. All right, when we were drawing all those lines of symmetry a few minutes ago, when we drew the one on the, or the ones on the little plus sign looking thing, and you drew this, then you drew this, you drew this, and then you drew this, guess what that point right there is called? Center of symmetry. And they all cross right at that one point. What if I'm looking at this shape? We have that point right there in the middle. That's the center, right? Center of symmetry. What turns is going to make it look exactly the same as it does right now?
Quarter.
Yeah.
A quarter of a turn, which we say is 90 degrees. What else?
180,
180.
270.
Now, be careful because this says only go up to 180. So just those two is all we do. That's our two answers. What's its rotational symmetry? It's got rotational symmetry at 90 degrees, got rotational symmetry at 180.
What about a circle?
Circle, what would a circle?
Maybe like 3.
Count that up for me, Hunter, tonight as part of your assignment, all right? And nobody else has to do it, just Hunter. See what the rotational symmetry is.
Really? He's gonna be counting forever.
How about this one? What would the rotational symmetry be on that? We turn it, 90 degrees again. What else?
180.
180.
I keep it 100.
How about that one? None, does it? It's not going to be the same. What if I did something like this? Yeah, stupid thing. Six-sided figure, if all those sides were the same, you put a dot right in the center. Is it just going to be 90? No. How can you figure it out? What's a whole turn? 360. How many corners does this have? 6. Divide that by 6. When we turn this corner, or I'm sorry, when we turn so that this side ends up on top, guess how many degrees it's going to turn? 60 degrees. Then another 60 degrees.
He's paper.
That's your assignment. Make sure my protractors get back where they belong, please.
Are we gonna need a break?
Stop recording. And so we don't like that recording.
Go up.
We don't stop recording.
I think I might have a break right now.
I gotta,
Can't see all that. Can everybody see that? It says 28,
40, 41.
40, and 41.
Let's do.
All right, on these examples, 90 degrees clockwise. So if we're going 90 degrees clockwise, if you look at your rules, 90 degrees clockwise says that you go, point starts A, B, or X, Y, whichever you prefer, it doesn't matter. And it switches it to B, and then the opposite of A. So you switch the two around, switch them, and then you take the second one and make it the opposite of what it was. So if we're looking at this, and as we go through this, I'm gonna write down over here A this time, because we're gonna need this for all four of these. A this time is 2, -2. And B is 1, 2, 3, 4, 5, 6, 7, 8, and down 1, 2, 3, 4, 5. So 8, -5. Those are our original points. All we're going to do to see where this new shape or where this new segment is going to end up, if we do 90 degrees clockwise, is we switch these two around. So for number 1, when we switch them around and take the opposite of the second one, we switch them, and we end up with -2, 2, but then we got to take the opposite of the second one, so we end up with that. That's going to be A prime. And then B prime is going to be, we switch them, you get -5, 8, but you need the opposite of the second one, so that's going to be -5, -8. So we got -2. Let me switch my ink color here. Try to get purple here. We got -2, -2, so -2, -2. That's A prime. And then -5, -8, so 4, 5, and down 1, 2, 3, 4, 5, 6, 7, 8. So B prime is going to be right there. And our new, if I could hit it, our new segment is right there. That looks horrible, but that's where it's going to be. So we rotated that 90 degrees clockwise. 90 degrees clockwise. So we took it this direction, 90 degrees. All right, next if we want to do number 2. Number 2, we got 180 degrees counterclockwise. So our rule for 180 degrees counterclockwise is AB goes to -A, -B. So we leave them in the same order, but we take the opposite of both of them. Remember to go back to the original shape. So we're taking this shape, the original, the red AB, and we're going 180 degrees counterclockwise. 180 degrees counterclockwise. So to get our A, we'll call this one A double prime and B double prime. We're just going to do that to each of these. So we leave them in the same order, but we take the opposite of both of them. So it's going to be a -2, +2 for A double prime. And then B double prime is going to be a -8 and a +5. So we go, let me change my color again here. We go -2, -2, +2. So that's A double prime. And then B is -8, +5. So 2, 4, 6, 8, +5. 1, 2, 3, 4, 5. It's going to be right there. That's going to be B prime, or double prime, sorry. B double prime. And our segment's going to look something like that. For C, if we go 180 degrees clockwise, you'll notice that it ends up, or it's got the same rule as 180 degrees counterclockwise, because whether you rotate it clockwise or counterclockwise, if you go 180 degrees, you go half a turn, you're going to end up the same place. So number three is the same as number 2. Number 3 is just the same as number 2. It's going to be in the same spot. If we go 360 degrees, when you turn it 360 degrees, so we're starting here, and we go 360 degrees, doesn't matter whether we go clockwise or counterclockwise, A is going to end up right back in the same spot, and B is going to end up right back in the same spot. So we just end up right back at the same. So the answer to number 4 is that segment where we started at. With rotational symmetry, a figure has rotational symmetry when it looks the same when turned. And again, remember, we're only going to turn it less than 100, or we're only going to turn it 180 degrees, not all the way around. So you're just looking at those angles where it has rotational symmetry for that. And when we write it, we're going to write it like you turned it 90 degrees, or you turned it 50 degrees, or whatever it ends up being when it looked exactly the same. How much of a turn you made it look, or it stopped and it looked exactly the same. Order of rotational symmetry. The order of rotational symmetry is when you take an object and you turn it one full turn. So we have an object and we want to turn it one complete turn. How many times does it look exactly the same as it did when it started? All right, so if it was just this cross-looking thing that I have here, we turn it all the way around and there's only going to be once. So the order of rotational symmetry would be just one time that it looks exactly the same. We're looking at this and we're trying to do rotational symmetry about this point right here. If we turn it, so we turn it and this corner ends up top right here, it's going to look the same. Well, what we turned it on, if you think about an axis going through here, we turned it 90 degrees. So it has rotational symmetry at 90 degrees, or with a 90-degree turn. And if we continue to turn it, and now this point ends up at the top, it's going to look the same. So it also has rotational symmetry at 180 degrees. Same idea on this one. If we look at the points here, maybe I put an X in that corner, a check mark in that corner, a squiggly line in that corner, and a circle in this corner. If we turn it so that the X ends up on top, we turned it 90 degrees and it looks the same, so it's got rotational symmetry at 90 degrees. We turn it so the O ends up on top, so the O would end up here. It's going to look the same, so we turned it half a turn, which is 180 degrees, and those are the places it has 90 and 180 degree rotate. Has rotational symmetry at 90 degrees and 180 degrees. This one, we look at the center point for it. It's going to be somewhere in there. Well, no matter how we turn this, it's never ever going to look the same until it gets all the way back around. So this does not have, there is no rotational symmetry for this shape. If we're looking at something like a hexagon, if I could draw a regular hexagon where all the sides and angles are the same, if we take this side, so if we have a center point here, and remember it's like you're on X and Y axes. So if this is on top, we want it to look exactly the same as when that's on top. Well, if we start to turn this and we turn it so that this side ends up being on top, it looked the same, but now we gotta figure out how much we actually turned it, because we didn't actually turn it a whole 90 degrees. Well, the way we can find that out is just by seeing what our order of rotational symmetry is. How many times in a full circle is it gonna look the same? And in this case, it's gonna be 6 times. It looks exactly the same. And we take that 6 and we divide it into 360. Well, 360 divided by 6, it goes in there 6 times. Goes in there 0, so it's 60 degrees. So when we turn this so that this point ends up right there, we've actually turned it 60 degrees. So at 60 degrees, it has rotational symmetry. If we turn it so that this point ends up right there, well, we've turned it this 60 and another 60, which is 120 degrees. And then if we turn it so that this point ends up right there, we've turned it this 60, and another 60, which is 180 degrees. So this shape has rotational symmetry at 60 degrees, 120 degrees, and 180 degrees.